Hello and welcome back to the November 2025 IB Chemistry TZ3 exam walkthrough. Wow, what a mouthful. If you're looking for the rest of the playlist, look there. It's there, going over all the questions. So this one's going to be questions number 16 through 20. So starting off with number 16, this is a classic highest boiling point. Anytime you see boiling point, we're thinking intermolecular forces. And so at some point you may need to think about certain types, but since with this one, all we have in all of these compounds is carbon and hydrogen. So that means that we're only going to be thinking about London dispersion forces. Okay. So with London dispersion forces, they're going to think about two things: is the mass, which is going to rely on the number of carbons in the chain. Obviously, if you London dispersion forces is essentially based on the creation of a temporary dipole. And so with your electrons, even though they are, because they are nonpolar, they are, there's no kind of distribution of charge. Is that essentially because everything's kind of moving, that they can be at an angle in which there is a temporary dipole that is formed between two molecules. And so if you have more mass, you have more electrons, and therefore the statistical likelihood that you're going to be at an angle to form a temporary dipole is going to increase. And so if you have a higher mass, you're going to have higher London dispersion forces. And if you have higher intermolecular forces, that means, your molecules very attracted to each other. Therefore, boiling point is you have to pull them away from each other because the distance between these molecules has to increase for it to become a gas. And so if you have more stronger forces, then it's going to require more energy to break them apart from each other, to overcome those intermolecular forces, and the boiling point is going to be higher. Okay? And so the first thing I'm going to do with all of these is just see the number of carbons for each. Okay, and so like this first one, we have 1, 2, 3, 4 carbons, a 4-carbon chain. Meanwhile, in the second one, we have 1, 2, 3, 4, 5, 6 carbons in this chain. Meanwhile, in the third one, we have 1, 2, 3, 4, 5, 6, also 6. And then in D, we have 1, 2, 3, 4, 5, 6, also 6. And so immediately, I'm going to rule out A. Okay, and so the next thing that we need to think about is branching, because all of these B, C, and D are going to essentially be branched isomers, okay, because they still have that 6th carbon chain, but the branches are going to be different, okay? And so in terms of London dispersion forces, once again, these are based on that temporary dipole. And so there's mass, but there's also surface area. And so if you have increased surface area, there we go. Which is going to be if you have a longer molecule, less branches compared to a shorter molecule with more branches. If you have a longer molecule, then once again, you're going to have higher London dispersion forces, because if you have more surface area, you once again have more statistical likelihood that your electrons are going to be at an angle in which a temporary dipole is going to be formed. And therefore, your boiling point is also going to be higher. And so immediately, I could draw out the structures of both C and D, but just looking at it, I can tell, that's a branch. That's a little 3 branch. But B is going to be our straight chain isomer, and therefore, since that is the straight chain, it's going to have the most surface area, and it's going to have the highest boiling point. So the answer to that is going to be B. Moving on to question number 17. Number 17 is which compounds can exist as stereoisomers. And so stereoisomers must contain one chiral center. And so something that has a chiral center is going to be a carbon that has 4 different groups. Okay, and so it must have at least one. And so if we draw out this 1, 2, and 3, is actually, if we can, so we have C for number 1, H, we have another C that is attached to a Cl, as well as a Br. And so since there's each carbon only has 2 attachments, that does mean that these 2 carbons must have a double bond in between them, because carbon, once again, likes to have 4 bonds. So that's number 1. Meanwhile, number 2 and number 3 is, so 2, you have C, you have H, you have Br, you have I, and you have Cl. And so that's it. That's all you got. Meanwhile, with number 3, you have C, you have H, you have Br, you have C, you have Cl, and you have Br. And this is just like number 1, where you must have a double bond in between. Okay, and so with first, we're going to ignore number 1 and 3 with the double bonds first and deal with number 2. And so with number 2, that carbon has a hydrogen, a bromine, an iodine, and a chlorine. That is 4 different groups. Therefore, this carbon is chiral. Therefore, you could draw 2 stereoisomers. I'm going to just draw it just kind of randomly. So I could either draw something like, I don't know, this is my wedge coming out in front of me. So like an iodine, boop. And then meanwhile, like a dashed Cl, an H, and a Br. And I could also draw another stereoisomer, which would be, if I mirrored this, it's an enantiomer. Those would be 2 different stereoisomers, okay? And so 2 would be able to exist as a stereoisomer. So for 1 and 3, we're not going to be going based off of enantiomers. We're going to be going based off of, for alkenes, the stereoisomers would be cis-trans isomers. And so the requirements for cis-trans isomers is that each carbon must have 2 different groups. And so this is going to be because if you have a cis isomer of something, that essentially means that with each of your carbons, your attachment with the highest priorities are in the same direction. You all don't know have to know which ones have the highest priority. You all don't really have to know how that works. But for this example, I kind of do have to say that, and you'll see why. But in the trans isomer, is your ones with the highest priority are on the opposite side of the double bonds. Okay, and so with number 1, with this CH2CClBr, is this carbon has hydrogen and hydrogen. Those are not 2 different groups. Even though this other carbon does have chlorine and bromine, 2 different groups, this carbon does not. Therefore, it does not have cis-trans isomerism, because no matter what, you would be having hydrogen on the same group as on the same side as either the chlorine or the bromine. Therefore, they wouldn't really be 2 different isomers. And so with 3 is you have this carbon. I don't want to draw that carbon with your hydrogen, your bromine, 2 different groups. Great. This carbon with a chlorine and a bromine, which is also great. You all don't have to know priority, but I still do just want to draw it. But you all don't have to know this once again, but bromine would have a higher priority. And so in this case with 3, you could draw 2 different stereoisomers, where you could draw one with your bromines on the same side, which would be your cis isomer. So this would be cis. And then you could draw bromine and your chlorine, and then your hydrogen and your bromine. And so in this case, your trans isomer would be where your highest priority substituents, so both your bromines are on opposite sides of the double bond. Okay, and so 3 could exist cis-trans isomerism, and so both 2 and 3 would be correct. So she would be the correct answer for that one. Okay, so number 18, this is IUPAC nomenclature, which is great. And so the first thing I'm going to do is identify what freaking functional group we have. And so we have this carbonyl group, this hydroxyl group. They have had a baby, and that is the carboxyl group, which has the class of carboxylic acids. And so carboxylic acids are named as enoic acid. And you actually forgot that. Once again, just test prep. These are... You have enoic acid, and then you have cool. So you have all of these. And so this is enoic acid here whenever it is an alkane, but you do have this double bond here. So it is going to be enoic acid. And I'm going to be honest, I never really taught this in the curriculum. But once again, it's in all the answer choices. So I do think they did that on purpose. And so this is where you do also need to remember that with alkenes, you do have the number of the carbon-carbon bond in the middle. And so in terms of numbering, our parent chain is we do need to have our carbon 1 starting at our carboxylic acid. And so that is because carboxylic acid is going to be our main guy, our main functional group that has the highest priority. And so we're going to start that at 1. And then we're going to go 1, 2, 3, 4. And at first I'm going to do that, but then I'm also going to do an alternate and see if I can number any other way to see if there's a longer parent chain. So I'm going to go 1, 2, 3, and I could go 4, 5. And so that would be higher. And so we are going to go that way. So let's erase that and make it the right one. So 1, 2, 3, 4, 5. And so now we're just going to figure out where our double bond is and where our substituent is. So our double bond is going from carbon 2 to carbon 3. So that does mean that we're going to have we're going to have what's it called? C2 enoic acid. Okay, because C2 is going to be the lower number out of these two, C2, C3. Meanwhile, our other substituent is going to be at carbon 3, so we do have 3 methyl. Okay, and then we also do have that our parent chain is 5 carbons. So that is going to be pent. So it's going to be pent 2 enoic acid. And so then we'll add our 3 methyl. So it's 3 methyl pent 2 enoic acid. And so that does get us that A is the correct answer for this one. So number 19, this is going to be, what is the sum of the coefficients when 1 mole of propan-1-ol undergoes complete combustion? So it's kind of just balancing an equation. And the sum of the coefficients just means that we're going to balance it and then just add these freaking numbers together. Every time I balance, I just put, where with combustion, it is a bit easier. And so with our carbon, C3 in our propan-1-ol, in our products, the only thing that has carbon is going to be CO2. So we're going to make that 3 CO2. Wow. And then we do have our hydrogen. And we have 7, we have 8 in our propan-1-ol. And so we do have H2O. That's the only thing that has hydrogen in it. Carbon dioxide does not. And so we're going to take that 8 and divide it by 2 just to get our coefficient there. And so that's going to be 4 H2O. And then we're going to see, wow, okay, we have our oxygens on our reactant side is we have just 3. And then on our product side, we have 6 plus 4. So we have 10. And so we're going to go over here and we're going to go, okay, we have 10. We're going to subtract 1 because we want this. It's 1 mole. So we want this to just be 1. We want to keep that there. So we need to make this add up to 9. Okay. And so we're going to just do 9 divided by 2. And so that's just going to be 1, 2, 3, 4, 5, 6, 7, 8. That's just going to be, in other words, 4.5. And so if we add up our coefficients, we have 1 plus 4.5 plus 3 plus 4. And so you have 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 12.5, which makes the answer to this one C. Yes, I do count on my fingers. Don't judge me. Okay, and for this number 20, this is just a simple Hess's law question. We have some equations with some known enthalpies of X and Y, and then we are asked to find it for this equation. And so literally what you do is you just look at what's in the reactants, what's in the products, and then change your equations accordingly. So in our reactants, as we have sulfur solid, that's in our first reaction, and it's 1 sulfur, 1 sulfur, and so that looks like it's all good. So we're just going to keep that as our same thing. We're not going to do anything to it at all. So we're just going to write sulfur solid plus O2 gas forming SO2 gas, and our enthalpy is plus X. Okay, so we're writing it out so we can make sure everything cancels out to get our right equation. And then our products is like O2 is in both, so we're just going to ignore it till the end. It should work itself out. In our products, we have SO3, and there we go, SO3. SO3 is in the products of the second equation, and so since it's already in the products, we don't need to like reverse the sign of Y. It's still going to be plus Y, but we do need it to be 1 mole. It is 2 right now, so we're going to divide both of them by 2. So we're going to get SO2 gas plus 1/2 O2 gas forming SO3 gas, and our enthalpy is going to be plus 1/2 Y. And so if we add these equations together, we do get that our SO2s cancel out. Our O2s, 1/2 plus 1, does end up being 3/2. Our products is 1, and so our enthalpies is going to be X plus 1/2 Y, which leads this to being B.